video, we'll talk about basic exponential, continuous time, and discrete time signals. And depending on the parameters that an exponential signal can take, it exhibits different behaviors. Okay, so you can derive, for example, periodic complex exponential signals if the parameters are complex. You can have real exponential signals. Okay, you can derive sinusoidal exponential signals. So frequently we're going to deal in our analysis of signal system with such signals, and we can use them to construct other signals. So the continuous time complex exponential signal is of the form, in general, is of the form c exponential e to the at. Now these parameters c and a in general could be real. They could be complex quantities. Okay. So the C and A are in general complex numbers, but they can be real. Okay, so depending upon the values of these parameters, the complex exponential can exhibit several different characteristics. Okay, so for example, if both C and A are real, then as illustrated in this figure below, you see if your A and C are real and A is a positive quantity. So in graph A, you have A that is greater than 0, then it shows a phenomena which is growing exponentially with time. Okay, so it is modeling a phenomena. For example, the signal is showing a phenomena which is in time growing exponentially. Okay, at t equal to 0, you can see that the signal takes the form of a constant, and that is c. Okay, that's not hard to see. For example, over here, when you substitute t equal to 0, then x of 0 is c. Okay, regardless of whether a is a positive quantity or negative quantity, real quantity or complex, at t equal to 0, the exponential is a constant. Okay, so that's the value at one point in time, that is t equal to 0. Okay, now the other case is for a less than 0. Okay, so if a is real, okay, c is real. You see, c is real, so we have a real axis over here. It's not a complex axis. For xt, this. The horizontal axis represents the independent variable, that is time in this case. The vertical axis is the signal, and we have both the axes as real. Okay, so we are dealing with the real exponential continuous time signal right now. So if a is less than 0, then we have a decaying exponential, right? So as t tends to infinity, xt goes to 0. Okay, so in this case, in the second case, as your t goes to infinity, then your xt, if your xt is of the form c of e at, this goes to 0 if a is less than 0. Okay, for example, it could be, for example, if c is 1, a is minus 2, so the e of minus 2t, as t tends to infinity, t becomes a large quantity, the exponential decay tends to 0 as the time progresses, right? Similarly, over here, in the first case, as t approaches infinity, as the time progresses, your exponential grows. Okay, if a is real and it's positive, so this tends to infinity. Okay, if that is the case. So as illustrated in these figures, if c and a are real, in which case xt is called a real exponential, there are basically two types of behavior. So if a is positive, then as t increases, xt is growing exponentially. Then if a is negative, xt is decaying exponentially. So also we note that for a equal to 0, xt is constant. Okay, xt is taking the value equal to c, which is a constant, and we said that for real exponential, c is also real, right? So it's a constant. The other thing to note is that, I mean, these signals, they, for example, if you have these signals can model the behavior of certain physical phenomena or processes. For example, in the first case, it could be a population growth with time, or you can say that this could represent the complex chemical reactions or chain reactions taking place in an atomic explosion, for example. So that is an exponential growth over here of showing the complex chemical reaction. So that can be modeled by real exponential signal as a function of time. Similarly, this a decaying exponential can, for example, model the radioactive decay. Okay, so as time progresses, the radioactivity is falling down. Okay, the other physical phenomena that can be modeled by such exponential decay are, for example, RLC circuits. Okay, for example, the energy storage LC tank, which is providing energy to a dissipative element, a resistor, is an example of this. Okay, where energy is being dissipated with time, or let's say a mechanical in a suspension system in a mechanical automotive system, where energy dissipates over time, can be represented by a decaying exponential. So over the period of time, the energy is being dissipated. Okay, and as time is progressing, the energy is decreasing. Okay, because it is being dissipated. We're going to encounter these exponentials time and again in analysis of signal and systems. Okay, so basically, if again, depending on this is the form, this is the generic form of the exponential signals, and depending on the parameters C and A, we'll have different behaviors. Okay, now this is real. We have discussed real real continuous time exponential signals. Okay, we can have complex exponential signal as well. So a second important class of complex exponentials is obtained by constraining A to be purely imaginary. Okay, so in case over here, you see if you constrain A to be purely imaginary, so that it doesn't have any real part. So over here you see that A is your purely imaginary quantity. Basically, A over here is j omega naught t. Okay, and this gives the exponential signal some interesting properties. For example, this exponential signal is periodic. Okay, this exponential signal is periodic, whereas the previous exponential signals that we have talked, the real exponential signals, are not periodic. Okay, they have nothing to do with the periodicity, because if you apply the transformation of time shift, okay, time shift xt, there is no time period that satisfies the given relation that xt is periodic in case if A and C are real. Okay, these are not periodic signals. They're not. However, if you constrain A over here to be purely imaginary quantity, okay, so A it's not j omega t, it's only j omega. Okay, it's only j omega naught. So if in this case A is j omega naught, then xt becomes a periodic signal. Why? Because you can expand this in a Euler's form, and you can write this in terms of sines and cosines, and you know that sine and cosine are periodic in nature. So you see, an important property of this signal is that it is periodic. To verify this analytically, we know that xt will be periodic if the period t, if there is smallest period t that exists such that the given relation holds, such that you can find the smallest positive quantity t that happens to be the period, which satisfies the relation that under the transformation of time shift, the signal stays the same. Okay, so either you advance it in time or you delay it in time, whatever is, I mean, depending on that real quantity capital T, if you can find the smallest positive quantity t such that you can still recover xt back, then the signal is periodic. Okay, so let's apply this equation to the complex exponential signal to verify if it is periodic, all this periodic. Then in that case, e j omega naught t, that's my xt, and if I add capital T in the argument, then I have this case. Okay, and this should be equal if it is periodic, right? So e j omega naught t plus t, and then you can bifurcate into two exponentials. Then this quantity should be equal to 1. Okay, so it follows for periodicity that we must have e j omega naught t equal to 1. And what are the conditions for that is that if the rate of oscillations, or omega naught a quantity which shows the frequency of oscillations, if it is 0, for example, if omega naught is equal to 0, then this is a trivial solution to the above equation, which shows that basically you are dealing with a constant, right? Then xt is equal to 1, which is periodic for any value of t. So regardless of value of t, this quantity is 1. But if omega naught is not 0, then the fundamental period t naught of xt that guarantees the equality in this equation, then that implies your omega naught if it is not equal to 0, will be equal to a quantity 2 pi by t, right? I mean, if you substitute this over here, then the things, they become like this. This becomes ej 2 pi by t into t, and this capital T happens to be the period, right? I mean, it satisfies this relation. So this t cancels out, and we're left with ej 2 pi. What is ej 2 pi? That's 1, right? If you expand this in a Euler form, then you have cosine 2 pi plus sine 2 pi, right? So this is cosine of 2 pi plus j sine of 2 pi. So j sine 2 pi is basically 0. So you don't have any imaginary term. All you're left with is a real quantity, because cosine 2 pi is 1, right? So this is 1. This is 1. Basically, this is equal to 1. So therefore, this condition that T naught equals to 2 pi magnitude of omega it implies that Ej omega naught T is indeed 1. Therefore, the complex exponential signal is always periodic. So you see, if A in the complex exponential signal, if A is real, C is real, then your real time or real complex or real continuous time exponential signal is not periodic, right? It's not periodic. You can see it from here in these figures. It's not periodic. But if the exponent A is constrained to be purely imaginary, the exponential becomes periodic because it consists of sines and cosines, right? And this period, if you're not dealing with the constant, unless you're not dealing with the constant, if omega naught is not equal to 0, then the fundamental period that satisfies the periodicity in general is 2 pi over omega naught, right? So that's the smallest positive value of t for which the above equation holds. Okay. You see, the reason for taking the magnitude is that it doesn't matter if A is positive or negative. You see, if I replace this by plus or minus, does it matter? No. You see, this will be plus minus, right? And even then, if I have this plus minus, it doesn't matter. The time period is still. You see, the idea is E minus j omega naught t, these two exponential signals, and E of j omega naught t are going to have same periods, right? Why? Because omega naught, what is t naught? Sorry, what is t naught? The time period. The time period is still 2 pi by omega. Okay, it doesn't matter what the sign is, because if you're going to substitute this for t in these equations, okay, let's move t naught from here. Anyways, this is going to give you, for this case, it will be E of minus j 2 pi, and in this case, it will be Ej 2 pi. You see, there is no difference between plus minus 2 pi, because cosine is an even function, right? It's an even function. Cosine minus theta is cosine theta. So cosine plus minus 2 pi is still 1, right? But sine plus minus 2 pi is 0. So minus omega or plus omega won't change the fact that xt is still periodic with the same period. So that's why you're taking the magnitude over here, right? That's the only reason. So, okay. Now, the signals Ej omega naught t and E minus j omega t have the same fundamental period. So a signal which is closely related to the periodic complex exponential is a sinusoidal signal. And you see, we can derive the sinusoidal signal from the generic expression of purely complex exponential signal. Okay, because this complex exponential signal can be expanded in Euler's in a Euler's form, in cosines and sines. And if you take the real part of it, it represents cosine. Take the imaginary part, it represents sine. So, and these cosine and sines are going to have the same frequency as the complex exponential is having. So, as illustrated in the figure below, this part represents, for example, with addition of phase phi in general, it represents the real part of the complex exponential, which is periodic, and it's having the same time period as 2 pi by omega naught. Okay, so I mean, if you're not going to add the phase phi, then this will start at 0, right? This is not going to start at 0. In fact, this is going to start at a. But owing to at t equal to 0, owing to a phase difference at t equal to 0, you see the amplitude is a cosine phi, okay? Because t is 0, it will make it a cosine phi. So the amplitude is a non-zero quantity, okay, but it's still less than a. It's a real quantity, but it's less than a because of the phase phi. But it doesn't matter. The general discussion is that the purely complex exponential signal can be decayed, can be decomposed into cosine and sine. This is the real part of the complex exponential signal xt. So when you're, for example, when with seconds being the unit of time t, you can guess what are the units for omega naught and phi are. Since t is in seconds, so that makes omega naught in radians per second. Okay, radian is a dimensionless quantity. It represents arc divided by the radius, so it's dimensionless quantity. Phase is represented as in radians. Okay, so radians per second multiplied by seconds is radians. So you can add radians to radians. Radians is a dimensionless quantity. So units of phi and omega naught are radians and radians per second respectively. So radians per second also represents the angular frequency. Okay, it's just like cycles. It's the angular cycles. So it is common to write omega naught also as 2 pi f naught being the units of cycle per second, or hertz, like the complex exponential signal. The sinusoidal signal is periodic with the same fundamental period t naught. Okay, and that's given by 2 pi by omega naught. So you see, by Euler's relation, the complex exponential can be written in terms of sinusoidal signals with the fundamental period, the same fundamental period as 2 pi by omega naught. Okay, so you can expand this in terms of cosine and sine, and we have seen the real part of it as shown in this in this particular figure. This is cosine. The imaginary part is a sinusoid. So similarly, from here, the sinusoidal signal is the imaginary part. This is the real part, and the imaginary part is a sine function. Okay. So if you take the real part, you have cosine. The imaginary part is a sine function. This particular form of xt, this particular form of xt can also be expressed in like this. Okay, so you can have a polar form of the magnitudes and the phases. It can be written in terms of periodic complex exponentials, again with the same fundamental period. The fundamental period is going to stay the same. These are just different expressions. For example, you can extract two sinusoids with the same period, or you can express xt again in terms of the polar form of the magnitudes. For example, over here, as cosine, you see cosine theta can be expressed in terms of exponentials as half ej theta plus e minus j theta, right? So that's what we are having over here. Okay. So you see this is where this half is coming from, and then you have in the argument omega naught t plus phi. So you can take one phi with the magnitude. So in this form of xt, the magnitudes of two complex exponentials. These are two complex exponentials. So these are the magnitude terms with coming with the complex exponentials. They become complex. Okay. So note that the two exponentials in the above equations have complex amplitudes. So alternatively, we can express the sinusoidal in terms of complex exponentials. So the real part is cosine, while the imaginary part is the sine. Okay. So I mean, again, these are different representations with the same period, and the period is 2 pi by omega naught. Okay. So you see different characteristics or different parameters of exponential signals. So what we saw earlier was that if a and c, these two parameters, if they are real or if they are complex, they give different attributes or characteristics to exponential signals. For example, if a is constrained to be purely imaginary, then the complex exponential is periodic. If it is real, if a and c are purely real, a could be positive or negative, then it's non-periodic. Okay, so different features, they come into the picture. So to discuss this a little bit further, you see the fundamental period t naught of a continuous time sinusoidal signal or a periodic complex exponential is inversely proportional to the rate of oscillations or the angular frequency omega naught, which we'll refer to as the fundamental frequency. So from the figure below, we see graphically what this means. So if we decrease the magnitude of omega naught, if we decrease the magnitude of the omega naught, then we are reducing the rate of oscillations, right? That is, we slow down the rate of oscillations and therefore increase the period. Exactly opposite effect occurs if we increase the magnitude of omega naught. So for example, over here, this omega 1 is greater than omega 2 over here, right? The rate of oscillations are high, so the frequency of occurrence is high. The number of cycles per second are higher. And similarly, this is still higher than the third case, which is omega 3. So omega 1 is the highest frequency. And in reverse fashion, you can see that if you increase the rate of the repetition or the frequency of the signal, sinusoidal signal, the time period is decreasing. So T1 is less than T2, okay, which is less than T3. T3 being the highest time period because the rate of oscillation are so slow that it takes longer for a cycle to occur, okay, to complete. So this figure shows the relationship between the fundamental frequency and the period of continuous time sinusoidal signal. So here omega 1 is greater than omega 2, greater than omega 3, so this is omega 1. In this figure, this is omega 2. Okay, these are all sinusoids, basically cosine functions. So sinusoid, sine, of cosine doesn't matter. But anyways, the idea is here that if you increase the rate of oscillations, the time period decreases, so it takes less time for the cycle to complete. But if as you go on increasing, you're on decreasing the frequency, the number of cycles per second, it takes longer for it to complete one cycle. Okay, so the time period is increasing. The time period is increasing in this manner. Okay, so T3 is greater than T2, T2 is greater than T1. Okay. Okay, now so let's consider the case where omega naught equal to 0. So if you recall, if you have a complex exponential signal xt as e j omega naught t. So let's bring the same form, the purely complex exponential. And if omega naught is 0, then we are dealing with the constant, right? This is again periodic with any value of t. So t is not defined. I mean, the idea is that when the rate of oscillations are 0, well, what is going on over here? In this figure, omega 1 is higher than omega 2. This omega 2 is still higher than omega 3 in this case. So as you go on in decreasing oscillations, it becomes a constant, okay? So the next could be like this, for example. And then it decreases. Then it becomes flat. So for that, you can have omega naught equal to 0. It's a constant, okay? So you see, the period becomes undefined. The period becomes undefined. So 2 pi by 0, time period is undefined for a constant, okay? So constants are not a periodic, they are not periodic signals, okay? So in this case, we mentioned earlier that xt is a constant, and therefore it is periodic. Actually, it is periodic. If you see it analytically, it is periodic with period t for any positive value of t. But the counter argument is that for periodicity, you need to have the smallest value of t, right? I mean, if it is periodic with t, then it is also periodic with 2t or 3t. But since t is not defined, then it is not periodic. So the fundamental period of this constant signal is undefined. So it's not periodic. On the other hand, there's no ambiguity in defining the fundamental frequency of the constant signal to be 0. That is, a constant signal has a 0 rate of oscillation. So if you, for example, if you give the DC, you connect a DC supply to the spectrum analyzer, you will see a peak at, so spectrum analyzer is going to give you the spectrum. It's not going to give you a time domain's representation of the signal. It's going to give you the representation of the signal in the frequency domain. And in the frequency domain, you will see that at f equal to 0, the strength is maximum because maximum energy is contained in the DC, and that's going to occur at 0 because the rate of oscillation is 0, okay? And the amplitude A is going to represent the strength of that DC. So you see the maximum energy of the signal is contained around f equal to 0, which represents the DC signal only, okay? It's not a low-pass signal, it's not a high-pass signal, it's purely DC signal. So DC has a 0 rate of oscillations. Therefore, the frequency is 0. The time period is undefined. Okay. So a periodic signal, in particular, the complex periodic exponential signal and the sinusoidal signal provide an important examples of signals with infinite total energy but finite average power. So you recall what is the, for example, if you consider this complex exponential, the energy, if you wish to compute the energy, you have to take the magnitude squared, okay, and then integrate it over the interval of time where it exists. For example, if you are going to do this in one period, okay, so let's consider this representation is going to consider this energy of the signal in one period. You have to take the magnitude squared, right? dt, so that represents the energy. And if you take the magnitude, then this quantity is 1, right? Magnitude of the exponential is 1. So this is T naught, okay? So T naught is the energy in one period, right? That's energy in one period. How about the other periods? Well, if you go on and if this sinusoid continues for, let's say, 10 years, 100 years, forever, the energy becomes infinite. However, energy is infinite, but the power is finite. Why? Because if you have to take the average over one period, T naught, then this is equal to 1. Since the average power is constant over one cycle, it's constant on the other, on the third, on the fourth cycle as well. So on infinite number of cycles, the average power stays the same. It's constant. So the complex exponential signals have finite average power. They are power signals, but energy is infinite. Energy is infinite. Okay, you can't go on integrating a constant infinitely, right? Because the time period is infinite. We consider this over one period, but in fact, the sinusoids, they're going to occur forever. So you have to consider infinite period of time to compute the total energy, which is infinite, but the power over one cycle stays finite, right? So for example, consider the periodic exponential signal, and suppose we calculate the total energy and the average power in the signal over one period. You see the energy is over one period is finite, but the power over the entire period where this phenomenon is occurring, where if you consider all the cycles, the power stays constant. Okay, energy goes to infinity if you consider the entire energy. Okay, so since there are infinite number of periods as t ranges from minus infinity to plus infinity, the total energy integrated over all the time is infinite. Each period of the signal looks exactly the same. So since the average power of the signal equals 1 over each period, averaging over multiple periods always yields an average power equal to 1. That is, the complex periodic exponential signal have finite average power. Okay, so if you integrate this from minus t to plus t, or minus t by 2 to plus t by 2, and you have to take the average, okay, and consider all the cycles, the average power stays constant, that is 1. Okay, but the energy E infinity is infinite. Okay, E infinity is infinity, and that is given by the magnitude of exponential signal E j omega naught t squared dt. And if you have to do this for minus t to plus t, and then you put the limit that this you wish to include all the cycles, okay, where it exists, then this goes to infinity. Okay, this is 1, and integrating 1 over infinite number of cycles is infinity. Okay,